Okay, in this screencast, we're going to talk about permutations and combinations. So we're looking at arrangements of things, right? Some people or items or numbers or letters or balls or whatever. So the number of ways we can just arrange them. And so this brings into our conversation permutations and combinations. Okay, so what we've got here is at the outset, the number of ways of arranging n distinct objects in a row is n factorial. So we looked at an example right at the start of the last screencast where, if we've got 8 people, 3, 4, 5, 6, 7, 8, and this is what kicked off our conversation and got us talking about this idea of factorial notation, this notation that, well, I want to be able to shorten this whole thing because I can see it's going to be an issue. I can see I'm going to need to use this a little bit. So like any abbreviation in mathematics, got to come up with a new symbol. They came up with this one because this is the wow factor. This is the one that puts exponential growth to sleep. This one, this absolutely kills it dead. It's the factorial growth. So factorial growth is mega, and so that's why we use the exclamation mark. But so 8 people in a row, 8 factorial. N people in a row, or n things, distinct objects. There's if they're identical, then there are adjustments made because we're not going to differentiate between A and A, right? There's no. If you switch them around, they're still A and A. So we're talking about distinct objects in a row, n factorial. So if let's just lay out A, B, and C, cards A, B, and C. So how many ways of arranging these 3 things? Well, the 3 factorial, I imagine, but let's have a look at them. Let's see what we get. So we could list them out as A, B, C in that order like that, but then we could switch the order of the C and the B, and sure enough, different arrangement. Then we could have BAC, couldn't we? And we could have BCA. And so for every starting letter, we get two options. Every starting letter, we get 2 options. Every starting letter, we get 2 options, and then we're just left with the one on the end. So it's 3 factorial, and 3 factorial is 6, and we've got, count them out, 1, 2, 3, 4, 5. So everything's adding up. Everything's looking good here. Okay, I just want to right now, because right at the top here we've got this permutations and combinations. Okay, so we have just, all we're doing here is we're looking at different order of 3 objects. This here is 6 permutations. So I'm gonna introduce this language now. 6 permutations. 6 permutations. Permutations, the difference between permutations and combinations. Permutations, if you know anything about the meaning of the word, permutations is just the different ways of ordering the same things. Right, that's permutations. Combinations are different groups. So with permutations, order is important. With combinations, order is not important. We're more interested in just the grouping. So whilst this is 6 permutations, they're the same 3 elements. So it's actually only one. It's only one combination. Now we're going to look deeply into this and the differences, but that's essentially it. Is that if we've got there's only one way of taking A, B, and C as a group, as only one combination, but there's 6 permutations. So that's the easiest way of explaining the difference is that order matters. Order matters. So therefore, order as in the order they appear in, A, B, C, and A, C, B, they're different because the order matters. And this one, B is in the 2nd spot and C is in the 3rd spot. So if you're arranging people in a row, of course order is important. But if it's just the grouping you're interested in and the makeup of the group and order is not important, then it's a combination. All right. So this is order does not matter. Order does not matter. Okay. So let's look at now let's just keep that. Let's just park that idea for a second. Let's have a look at another type of example. Let's look at taking 5 5 cards, right? Let me set this up. Okay, so I've got 5 cards here now, A, B, C, D, E. And what we're going to do is we're going to choose 3 cards, and we're going to look at the number of ways we can do that. So we're going to choose 3 cards from 5. Okay, so we're going to choose 3. So what are the combinations? And we need to be careful of how we say this. What are the combinations that we can come up with? So how many can we come up with? And it does, again, matter, doesn't it? Is the order important? So if we've got 3 slots, right, we're just going to select 3 of these guys. How many ways can we do it? How many ways can we do it? Okay, so we can plonk any one of those 5 into this first position here, can't we? All right, I can put in A, B, C, D, or E. All right, once that card has gone in, then I've got 4 to choose from for the second spot, and then I've got 3 to choose from for the third spot. Now, I'm not arranging all 5. 2 of them are being left out. So this is not 5 factorial. This is 5 times 4 times 3. Now, if I wanted to write that in factorial notation, well, it's 5. I've got 5 factorial, but I'm going to have to chop off the 2 and the 1, aren't I? Or I could write it as 5 over 5 minus 3, and that's just using the numbers that I was given. 3 cards from 5, okay? So this is, well, I know what it is. It's 5 times 4, 20 times 3 is 60. So that means I've got 60 ways that I can select 3 cards from 5. Now, is that permutations or is that combinations? Well, if you think about it, then this group of 60 will be, if we started to write them out, it'd be A, B, C, it'd be A, B, D, it'd be A, B, E, it'd be B, A, C. So we would be including the same elements but in different orders. So yes, this order is important. This is a permutation. Now, in order to calculate a permutation, we take, all right, so for, let's just hold off on how to calculate it generally for a second. If we wanted just to take one of these, so I've started here to list out some of the 60, right? There's first 6 of the 60 permutations that I could produce. If let's just extract one of these, right? Let's extract the ABC. Let's just extract him out. And how many ways could I write ABC, but just in different order, right? So I could write it obviously as ABC. I could write it as ACB. I could write it as, sorry, I need to start with a B now, BAC. I could write it as BCA. I could write it as CAB, or I could write it as CBA. So with just one of these collection, with ABC, just with those letters, there are 6 permutations for one combination. 6 permutations for every combination. So if I just pulled out BDE, then there would be 6 ways that BDE could be arranged in different order, 6 permutations, but only one combination. So if I'm interested in how many combinations there are, so this 60 represents 60 permutations, because order is taken into account with these 60. All right, 5 by 4 by 3. We're not considering, once we put that first letter in, and then the second one goes in and the third, the order is taken as different. So we are counting, we're counting all of these. Right? We're counting ABC, ACB, they're counting them all as different arrangements. Right? But for every combination has 6 permutations. So how many I'm going to divide by 6 permutations per combination. So therefore, we have 10 and only 10 combinations. And the combinations are going to be dead easy to write out. Okay, so there's our 10 combinations. I just paused and wrote those out. So you can see here, if we just go through, we've got 6 of them start with A, and then 3 with B, and 1 with C. But they're all the combinations. There are no more combinations. But peeling off each of these combinations, there are another 6 permutations. Off each of these, times 6 perms. For each of these combinations, there are 6 permutations. You get the idea. So this is the difference between permutations and combinations. Many, many, many more permutations. If order is important, then the likelihood of picking an order much harder. So, okay, so how do we represent this using factorial notation then? So for the permutations, it was simply for 3 cards from 5, it was 5 over 5 minus 3, so 5 factorial over, 5 factorial over 5 minus 3 factorial, got us 60. What do we need to do to that in order to make it a combinations? So we would say that the number of combinations, so the number of combinations, therefore the number of combinations in factorial form would be 5. Now we need to divide by 6, right? So we're going to divide by, that's 3 factorial, isn't it? 3, 2, 1 over, by 5 minus 3 factorial. So there's our number of combinations for 3 from 5, number of combinations, and here is our number of permutations of 3 from 5. So in a general sense, so if we wrote generally, okay, so if we look now generally, okay, so the number of permutations of R objects from N. So we're taking a subset of R from a parent group or a larger group of N. Then this is the number of ways we can do that. NPR, standing here for permutations, where remember order matters. So this P here, right, that's permutations. And that's where order matters. And that is found by n factorial over this. Right, the C here is where order does not matter. Order does not matter. And that's for NCRC, standing for combinations. The number of combinations of R objects from a larger group N will be this. Now, because of this R factorial down here, this is going to be a smaller number. We're dividing by the larger denominator. Okay, so let's do. Let's run the example. So the one at the top was arranging. So if you're arranging, what was it? 6. What do we do? Oh no, that was just 3. Yeah, we are 3 cards in a row. So that's just the number of arrangements of 3 cards in a row. That's just 3. From 3, we're arranging 3, but it's a permutation. So that's so how would we write this? We write it as 3 factorial over 3 minus 3 factorial. This is where our 0 factorial comes in. 3 factorial over 0 factorial, which we've just learnt to be 1. 0 factorial is 1, so that's 6. So that's the number of permutations. That's how many ways of lining 3 people up. But if we want the combinations of 3 from 3, then that's where we've got 3 factorial over, well, it's 3 factorial by 3 minus 3 factorial. So I end up with 3 factorial over 3 factorial, which is just 1. So that's 6 permutations and 1 combination, just to highlight that distinction between those two ideas. Okay, let's do some examples. Okay, so let's do some examples. All right, so in how many ways can the letters of the word candle be arranged? Okay, so is order important here? Clearly, how many ways can the letters be arranged? So we're just rearranging the letters. It's a triviality if it's the combination we're after, because every rearrangement spells or looks different, right? So this is definitely a permutation. So how many ways can we arrange essentially 1, 2, 3, 4, 5, 6 things in order? Well, we can write it as, well, that's 6 things from 6, but actually in this sort of question, we normally just cut to the chase and say, well, that's 6 factorial, and 6 factorial is 720. So it's an alarming number of ways of doing things with just 6 items. So in part B, in how many ways can a group of 4 boys and 3 girls be arranged? Well, this is 7 people. There's no stipulation about how they should be arranged. We can just arrange them however we like. So this is a similar question, and it's just 7 people in a line. So we can arrange them in 5,040 ways because they're distinct. They're different. Boy 1, boy 2, boy 3, boy 4, girl 1, girl 2, girl 3, all different. So same with 7 books on a bookshelf. How many ways can we arrange those? It's a surprisingly large number. In how many ways can a group of 4 boys and 3 girls be arranged if no girls are to be next to each other? This requires a little bit of technique. So the girls can't, so there's 4 boys and 3 girls. So the girls can't be next to each other. So the best way and sometimes it's just, you've just got to sit back and have a look at a technique and then use it when you see this sort of question, because this is quite a common type of question. So if we've just got 4 spots for the boys, right? Maybe I should have just given them a big old B for boys, right? 1, 2, 3, we've got 4 boys, haven't we? Now they can be arranged in that order 4 factorial ways, right? I'm going to put big circles around them, big buffer zone around the boys. Now the girls, no girls will be next to each other, so we can't have girl, girl. So the girl options here are, well, they can go into this position here, or into any of these little gaps between the boys. Okay, so I've got 3 girls, and I can put them into any of those 5 gaps. So how many ways are there of choosing those 3 gaps for those 5 girls? And is order important here? So, well, no, it's not, because if I choose gap 1, 2, 3, it doesn't matter if I switch the order of that. It's really just the gaps where I position these girls. So the question is really, how many ways can I position these girls so that they're not together? No girls would be next to. So there's one way, but basically I've just picked 3 spots out of 5 where order is not important. So there are 3 ways of placing the girls, but then once we place them, well, there are 3 factorial ways of arranging those girls in that line from left to right. And as we just talked about at the top of this question, there are 4 factorial ways of organizing those boys. So 3 factorial by 4 factorial by 5c3. Now 5c3 is 5 factorial over 3 factorial, 2 factorial. Times this by 3 factorial, times this by 4 factorial. I'll do a little bit of simplifying here because that's what I like to do. Now 4 factorial and 2 factorial, I can do a little bit with that. I can rewrite this as 5 factorial times 4 times 3 times 2 factorial over 2 factorial. And I can just make this a little bit smaller. So I end up with 5 factorial by 4 by 3. 5 factorial is 120. So 120 by 4 by 3. 120 by 12. 120 by 12. And 12 12s are 144 with a 0 in the end. So 1,440 ways of arranging these 4 boys and 3 girls such that The girls cannot sit together. So that's quite complex. You're going to see some questions like that. Typically, these types of questions range. They do go from very straightforward to very hard very, very quickly, just to try and understand. But like a lot of these areas we're covering at the moment, it's going to feel really unstable as you try and work your head around some unfamiliar problems, but be patient. How many 4-digit numbers? All right, so another example. How many 4-digit numbers can be made using each of the following digits only once? So this is another very popular type of question. And so 5, 6, 7, and 8, we've got 4-digit numbers. Okay, so I've got 1, 2, 3, 4, the 5, 6, 7, and 8. Well, every is order important? Well, yes, because 5, 6, 7, 8 is 5,678, whereas if I switch 6 and 5 around, it's 6,578. That's a very different number. So order is important here. So this will be just 4 factorial. So A will just be 4 factorial because we're just finding all the different ways of arranging these distinct numbers so that we get a different number. So 4 factorial giving us 24. Okay, in the second example, 5, 6, 7, 8, and 9. So now we've got 5 digits here to slot into 4 places. So we've got 4 spots, 1, 2, 3, 4, and I've got these 5 digits to get in there. So I'm going to have to choose 4 from those 5. Now the question is order important? Well, again, it's a number, isn't it? So yes, it is important. So that's 5p4, and 5p4 is 5 factorial over 5 minus 4 factorial. 5 minus 4 factorial. Now that's just 5 factorial over 1. So that's 5 factorial, which is 120. So 120 ways of doing that. And part C, 7, 8, 9, and 0. So the difference with part C is that, right, we've got a 4-digit number, so we can't lead with the 0. So I can only put 7, 8, or 9 in here. So I've got a choice of 3 digits. All right, so 7, 8, or 9 can slot in there. So it gives me a choice of 3. Once I've got those 3, now 0 comes back into play now. So I've got 3 more to choose from for the second slot. And then I've got 2 and 1 position left. So that gives me 18 permutations, 18 different 4-digit numbers I can make with those 4 digits. Okay, and final example is right here. Okay, so I've got a mixture of boys and girls, 8 boys and 5 girls who attend the senior maths club. Find how many ways the teacher can choose a team of 6 students. Okay, so let's consider this. We've got 13 students and they're split into 8 boys and 5 girls. This is a very, very common question. So we're choosing 6 from 13, and part A says there are no gender restrictions. So in A, all we're doing is selecting 6 students from 13. So the question is, 6 students from 13, do I put a C in here or a P? Is order important, or are we just interested in the group? So if I have 6 students, do I want to differentiate between the order of those students? Well, this is just these kids are just going to represent the school in a competition. There is no order, it's just a team. So this is order is not important, so it's 13C6. Okay, it might be time to go into our calculators and work out how they are important to us in this calculation. So 13C6, we go in here and we will find under menu, we're in the calculator mode. Under menu, we go to 5, probability, and there you can see permutations and combinations. So I hit 3 for combinations, and it comes up with this NCR notation. So I'm now going to put 2 numbers in separated by a comma. I'm putting in 13 and then a comma, and I'm choosing 6 from 13, I believe, and hitting enter. So 1,716. 1,716 is my answer. 1716. Okay, now in part B, things change a little bit. We get some conditions. We now do want an equal number of boys and girls. So we want 3 boys and 3 girls. So in this case, now we've got 8 boys, so we look at the 2 subsets. From those 8 boys, we want to select 3. Again, order doesn't matter. And from the 5 girls, maybe I'll hold off on that. From the 5 girls, I need to select 3. So for each of those, so there's a certain number of ways of being able to choose 3 from 8, and there's another number of ways of choosing 3 from 5, and that's those numbers there. So for all of these combinations of boys that I can come up with, I can come up with these combinations of girls. So I need to multiply these 2 numbers together. 8C3 by 5C3, and that gets me 8C3. Let's go back to the calculator. 8C3 by 5C3. So remember what it was. It's menu 5, 3. Gets you there quickly. So we hit 8, 3. We get out of there. We hit times, and then we want to go back into menu 5, 3, and it was it 5C3 here? 5, 3, and enter. So 560 is our number of ways of choosing 3 boys and 3 girls. And part C asks at least 2 of each gender to be included in the team. So there are a number of combinations here, team combinations that work. So we can have 2 boys and 4 girls. So we can go ahead and work that out. We can have 3 boys and 3 girls. And that's what we've just worked out. We know that there's 560 there. So that gives me 560. And I can have 4 boys and 2 girls. Right, remember, I've got 6 in my team, haven't I? 6 in my team. And I've got to have at least 2 of each gender. So these are the 3 scenarios at work. 2 boys, 4 girls, 3 of each, 4 boys, 2 girls. I don't think there's any other combination. So we need to work out for each of these how many combinations there are. So from 8, I'm going to choose 2 boys, and from 5, I'm going to choose 4 girls, and that'll be the number of combinations there. I already know 3 and 3 and 3, and for 4 boys, there will be 8C4 by 2 girls will be 5C2. So I need to calculate these, and then we're going to add them all together. So to the calculator we go. So it's 8.2 by 5.4. So again, it's menu 5.3. So it's 8.2 times menu, what was it? 5.4. So menu 5.3. And then it's in here, it's 5.4. It's choosing 4 girls from a group of 5. So that gets me 140. While I'm in here, I'm going to calculate menu 5.3 for, what was it, 4 boys, so 8.4, and that was to be multiplied by menu 5.3, and this is now, what are we choosing from 5 girls? We need to choose 2. So there are 700. So 140 and 700 make up those numbers. 140 here, 700 here. And so if we add those 3 together, we get 0, 4, 10, carry the 1, 2, 7, and 7, 1,400 combinations of teams, 1,400 teams, such that we've got at least 2 of each gender in that team. Cool. All right. So that means we're okay now to continue with exercise. What was it? Exercise 1H. Exercise 1H. So exercise 1H, and we can now do questions 5 through 12.